Hello friends, welcome to CEC Live Lectures. Dear friends, today in this session we are going to continue further on carboxylic acids. So we had a discussion on carboxylic acids in our previous session where we discussed a lot so that you are benefited. Friends, taking your benefit into account, today also we are going to talk more. In the first half we are going to talk on the methods of preparation of carboxylic acids as well as the physical properties of carboxylic acid, and in the later half we are going to discuss on acidity trends. For the discussion on the topic, we have with us in our studios Dr. Aparajita Chauhan. Dr. Aparajita Chauhan is Associate Professor in Department of Chemistry in Sri Aurobindo College, University of Delhi. And Dr. Aparajita Chauhan is a prolific professor. She has authored numerous books and her books are admired by the students community as a whole. Friends, if you wish to ask questions from Dr. Aparajita Chauhan, you can contact us through our toll-free number. Our toll-free number is 1-800-110-430. I repeat, our number is 1-800-110-430. All dear friends, if you wish to ask questions from Dr. Aparajita Chauhan on today's topic, then you are requested to call in the last 10 minutes of the lecture so that first you could understand the methods of preparation of carboxylic acids, their physical properties as well as acidity trends. Now I would like to welcome our guest Dr. Aparajita Chauhan once again. Hello ma'am, welcome to the lecture.
Welcome viewers. In our last lecture on carboxylic acids, we had done the nomenclature and common names of carboxylic acids as well as the natural sources of carboxylic acids, where they occur in plants and few animals, and we had done also the methods of preparation. While we were doing methods of preparation, we saw that carboxylic acids can be prepared by oxidation of primary alcohols. They can also be prepared by oxidation of alkenes and alkynes, and the arenes which have benzylic hydrogen in them also undergo oxidation with acidic KMnO4, resulting in the formation of benzoic acid. We had touched upon carbonation of Grignard reagent, which also results in the preparation of carboxylic acids. So today we shall be discussing this further and we will be doing this reaction in detail. So in the previous lecture, what we've seen that when we do oxidation of primary alcohol, that is benzyl alcohol, as well as when we do oxidation of toluene, and what we find in toluene is that it has benzylic hydrogens in them, that is the methyl group has benzylic hydrogens. These on oxidation with KMnO4 gave us benzoic acid. Now to continue further, now if I talk of carbonation of Grignard reagent, then this is a very good method for preparation of carboxylic acid. Now let us start with alkyl halide, and what we see is that when we treat an alkyl halide with magnesium, solid magnesium in ether, it results in the formation of Grignard reagent. Now this Grignard reagent is an organometallic compound. So in this case the carb anion is formed, and this carb anion acts as a nucleophile and it reacts with carbon dioxide, which we take in form of ice, and this dry ice, and in the carbon dioxide what we observe is that the carbon is attached to two electronegative oxygens, and these electronegative oxygens pull the electrons towards itself. As a result, that this carbon is electrophilic in nature. Now what happens is the carbon ion is attracted towards this electrophilic carbon, resulting in the formation of a carboxylate salt. Now this carboxylate salt on hydrolysis, acidic hydrolysis, gives us a carboxylic acid. So what we believe that in the overall transformation of an alkyl halide to carboxylic acid, it is a step up method. For example, if I start with bromocyclohexane, then what we find is that in bromocyclohexane, this molecule has 6 carbons in it, and when it undergoes reaction with magnesium, resulting in the formation of Grignard reagent on carbonation and acidic hydrolysis gives us cyclohexane carboxylic acid. The thing to be kept in mind is that the starting compound is having 6 carbons, whereas the acid is having 7 carbons in it. So this is a very important method for going up the series. Not only this, what we find is that this method has a important synthetic use. For example, now I have taken 2 examples in this, and in one we've taken para-bromotoluene, and when we talk of para-bromotoluene, we want to convert para-bromotoluene to taulic acid. Now please remember that it is the halo part which will be converted into Grignard reagent. So when we do the reaction of this molecule, that is para-bromotoluene, with magnesium in dry ether, it is converted into Grignard reagent, and this on reaction with dry ice followed by acidic hydrolysis results in para-toluic acid. So when we have to introduce a COOH group, please remember, and the starting molecule has an halide group in it, we will play with the halide group, that is, we will do the reaction here, convert it into Grignard reagent, which on reaction with CO2 followed by acid hydrolysis will be converted into a carboxylate group. Now if I look into the second example, I have taken these 2 examples purposely. Now here we want to introduce a carboxylate group in the side chain. That is, we want to convert toluene into phenyl acetic acid. So we are converting one of the benzylic hydrogens and replacing it with a carboxylic group. So what we do in this case is we do the reaction with bromine at high temperature or with bromine in presence of UV light. When it undergoes free radical reaction, substitution reaction, and one of the hydrogens here is replaced by a halogen, resulting in the formation of benzyl bromide. Now this benzyl bromide on reaction with magnesium results in the formation of Grignard reagent. This Grignard reagent on reaction with dry ice followed by hydrolysis gives us a phenyl acetic acid. So now what you have to remember here is that while you're doing a conversion, or they ask you to complete the reaction, that is, they start with Grignard reagent and give us dry ice as well as and followed by hydrolysis. What you have to remember is that we are going to replace this MgBr part of the substrate with a carboxylate group, and in this case we are going up the reaction. Not only this, what we find is that carbonation of Grignard reagents will also result in the preparation of branch chain carboxylic acids, which is otherwise difficult to prepare. Another very important method of preparation of carboxylic acids is hydrolysis of nitriles. And again we can now start the reaction from an alkyl halide, that is, we do the reaction of an alkyl halide with sodium cyanide, alcoholic sodium cyanide, or with NaCN in acetone. When it undergoes, alkyl halide undergoes nucleophilic substitution reaction and the Br is replaced with a nitrile group. Now when we look into this, when we do the hydrolysis of a nitrile, what we find is that this hydrolysis of nitrile, the complete hydrolysis, whether we do the acidic hydrolysis or basic hydrolysis, results in the formation of a carboxylic acid. So now what we observe here is, now if you look into the structure of C and N, then what we observe is that C is bonded by a triple bond to nitrogen. That is, C is making, carbon is making, the nitrile carbon is making 3 bonds with nitrogen. And when we look into the carboxylic acid, then we've seen when we in the structure of carboxylic group that carbon is attached to 3 atoms of oxygen. That is, two atoms of oxygen. In one it is forming a double bond with oxygen, and in that is the carbonyl group, and the other case it is forming a single bond with the hydroxyl group. So in the whole reaction what we are doing is we are breaking three bonds between carbon and nitrogen, and this carbon is making three bonds with oxygen atoms. So now if we look into this reaction, so what we find is that if we treat benzyl bromide with NaCN and acetone followed by acidic hydrolysis, we will get phenyl acetic acid. So in this case again we've gone up, we are stepping up the reaction. That is, the starting compound had 6 carbons in it, whereas the product has, the starting compound had 7 carbons in it, whereas the product has 8 carbons, 1, 2 and 6 carbons from the benzene ring. Now if we talk of the mechanism of this reaction, then what you have to remember is that when we do acid hydrolysis of a nitrile, first we will get an amide, and then this amide undergoes further acid hydrolysis to give us a nitrile. So when we talk of this reaction, now when we talk of, if I look into this structure, what we find is that this carbon is slightly electrophilic in nature, and when we do the reaction with water, water is also a weak nucleophile. So this reaction will not be feasible. So in terms that we want to increase the rate of the reaction, our first step is going to be protonation of this nitrogen, so that we can convert this nitrile into active nitrile. So while we are doing the reaction, the mechanism of the reaction, we will be seeing that in the whole of the mechanism, it is the solvent molecules which are playing very important role. That is, either as a water molecule or as a hydronium ion. So what we observe here is in that in the first step, this nitrile undergoes protonation and is converted into activated nitrile. So in this case, when it is converted into an activated nitrile, now what we find is that this carbon has a positive charge. So now it is strongly electrophilic and it will react with a new weak nucleophile, which is water. Now water acts as a nucleophile through lone pair of electrons on oxygen, and this oxygen makes a bond with electrophilic carbon. As a result of which, oxygen has a positive charge on it. Now in the next step what happens is there is a proton transfer, and when we talk of a proton transfer here, then what we see is that this proton transfers from here to this nitrogen, and this double bonds goes back here on the and collapses. These electrons collapse on the oxygen, neutralizing the double bond, neutralizing the positive charge, and this hydrogen goes on to this nitrogen here. But now what we observe is, which the structure which I have not shown here, that the lone pair of electrons on oxygen undergo resonance with the pi electrons here, resulting in a double bond between carbon and oxygen, and these electrons go on the nitrogen atom. Now when this oxygen has a positive charge on it, on this, and it results in the enol form, and now this oxygen will lose a proton from here, resulting in the formation of amide, which I have shown in the next reaction. So now what happens here, that these lone pair of electrons, as I've said earlier, undergo resonance with the pi electrons here, as a result of which this oxygen has a positive charge on it, and the bond between the O and H becomes weak, and this hydrogen undergoes deprotonation, resulting in a double bond between carbon and oxygen, and hence forming a propanamide. So what has happened in this reaction is that the enol form has converted itself into a amide. Now please remember, we will do further hydrolysis of an amide when we will get a carboxylic acid. So that means when we do partial hydrolysis of a cyanide, we will end up getting an amide. Now if you will watch carefully in the upcoming slides, then what we find is that we are repeating the same sequence of events. That is, first of all, that what we have to do is we have to increase the electrophilicity of the amidocarbonyl compound. For that, this oxygen undergoes protonation, and when this oxygen undergoes protonation, these electrons from here go on the oxygen and the carbon has a positive charge on it. So this carbon has become electrophilic in nature, and now it will react with a water molecule which is a weak nucleophile, resulting in the formation of a tetrahedral intermediate. Now in the next step, our objective is to remove this proton, which is removed when it reacts with a water molecule here. It will undergo acid-base reaction. This H will be given off as proton and water will act as a base, and this electrons will collapse on oxygen, resulting in a neutral molecule here, that is a neutral tetrahedral structure here. Now our objective is that we have to convert this amino group into a good leaving group, because once we replace the amino group, we shall be able to convert this into a carboxylic acid. So now what happens is, when we did the previous reaction, what we found was that this goes back here, this hydrogen proton reacts with water, and in that consequences of that is that it forms a hydronium ion. Now here again there is an acid base reaction between a hydronium ion and the amino group here, and the protonation of this amino group takes place, and the amino group is converted into NH3 positive. Now in the next step, what we have to do is we have to remove the NH3 group. Now what happens is, this is facilitated by the OH present here. What happens is that one of the OH gives its electrons back. There is a back bonding here between the oxygen and the carbon, and this ammonia, this leaving group, is pushed off as neutral ammonia here. Not only this, now when it makes a bond here, this oxygen has a positive charge on it, and since this has a positive charge on it, it can easily undergo deprotonation, and now this ammonia acts as a base and it deprotonates this OH, converting it into a carboxylic acid, and in the whole reaction one equivalent of ammonium is liberated. So what we have to remember now is that when we are doing hydrolysis of nitriles, we have to convert the CN group into a carboxylic group. If we are doing partial hydrolysis, we will get an amide, and if we do complete hydrolysis, then we will get a carboxylic acid. So if we are doing the reaction of propane nitrile and we are doing acidic hydrolysis, then what you have to remember is that propane nitrile will be converted to propanoic acid. Now let us quickly review what we've done till now with the help of few examples. Now for example, we have this molecule 1, 2, 3, which is propyl benzene, and what happens when propyl benzene is treated with KMnO4? So what you have to remember is, when we are doing the reaction here, as long as the benzylic carbon has benzylic hydrogen in it, it will be oxidized to a carboxylic group. So what we find here is that the whole of this chain will be converted to a COOH, and this molecule will result in the formation of benzoic acid. Next, if we take benzonitrile and do the hydrolysis of benzonitrile, then as I have just said, this CN group will be converted into a carboxylate group. The next reaction is the reaction of Grignard reagent with carbon dioxide. So what you have to remember here is that this is a step-up reaction in which the acid will have one carbon more than the starting compound. And what you have to remember here, in short, if they are not asking you the mechanism, we have to replace this MgBr with COOH with a carboxylate group, and what we'll get here is a phenyl acetic acid. Now let us look into the structure of carboxylic acid. We have to discuss the physical properties of carboxylic acids, and for doing so it is very important to understand the structure of carboxylic group. So now if I look into the carboxylic group, what we find is that carboxylic group is made up of two parts. One is the CO part, where this carbon is attached to an oxygen or bonded to an oxygen by a double bond, which is a carbonyl group, and in the other side this carbonyl carbon is attached to a hydroxyl group, and this carbonyl carbon is sp2 hybridized. Since it is sp2 hybridized, what we find is that the arrangement of atoms around this carbonyl carbon is planar, and the bond angle is nearly equivalent to 120 degrees in all the cases. So now what we find is not only this, when we look into the molecule, what we find is that this carboxylic group is highly polar, since it has two polar groups in it. One is the hydroxyl group. Why is the hydroxyl group polar? Because in this, hydrogen is attached to an electronegative oxygen. Since hydrogen is attached to an electronegative oxygen, this bond will pull the electrons towards itself, as a result of which this bond becomes weak, and this hydrogen can be given off as proton. So we'll say that carboxylic acids are acidic in nature. Not only this, this negative charge undergoes resonance with the pi electrons here, and what we find is that the other center of electronegativity is the carbonyl oxygen. So what we find is that in this molecule we have two electronegative centers. One is the carbonyl oxygen and the other one is the hydroxyl oxygen. And we have two nucleophilic electrophilic sites in it, that is the carbonyl carbon, which has a positive charge on it, and this hydrogen is also having a positive charge on it. The second point that is to be noticed is that this oxygen can accept a proton, and this hydrogen can accept a oxygen, or it can react with an electronegative atom. So what we find is, exploiting this property, what we find is that these acid molecules are capable of forming strong intermolecular hydrogen bonding through this oxygen, which can bond with a proton, and through this proton, which can bond with an oxygen. So that means this hydrogen can bond with this oxygen, and at the same time this oxygen can bond with this hydrogen. So this results in the formation of dimers. So what I've shown here is dimer formation. That is, if I look into one carboxylic acid, C bonded to a double bond O, and now this O is capable of forming intermolecular hydrogen bond with the hydroxyl group of the second carboxylic group, and the carbonyl group of this acid is capable of forming intermolecular hydrogen bonding with the hydroxyl group of the first carboxylic group, resulting in the formation of dimers. And the intermolecular forces hydrogen bond between these is so strong that even when we distill acetic acid, these bonds do not dissociate. And therefore what we find is that carboxylic acids have high boiling point because of the dimer formation. And if now we compare the boiling point of acids with other organic compounds having comparable molecular mass, then what we find is that carboxylic acid, if I talk of propanoic acid, its molecular mass is 74. And if now I compare it with pentane, whose molecular mass is 72, diethyl ether, whose molecular mass is 74, butanol, whose molecular mass is 72, 1-butanol, molecular mass 74, and propanoic acid, of course, molecular mass 74. In spite of having same molecular masses in the same range, there is a vast difference in their boiling points. Why is it so? We know that alkanes are non-polar in nature. Since alkanes are non-polar in nature, the forces of attraction between them are van der Waals forces. And we find that pentane is gas at room temperature. Similarly, diethyl ether is also a gas, and both the boiling points of both these molecules or compounds is 35 degrees Celsius. When we talk of butanol, then what we find is that there is lot of difference. The boiling point of butanol is almost double to that of pentane and diethyl ether. It is because of van der Waals. It is because of dipole-dipole interaction in butanol. And when we talk of butanol, in butanol is an alcohol. There is intermolecular hydrogen bonding between the alcohol molecules, between the butanol molecules, and the boiling point is 118 degrees Celsius. But when we talk of propanoic acid, then what we find is, as I have already discussed, that in this case there is dimer formation and the boiling point of propanoic acid is highest, that is 141. So what we see is that the structures and the molecular forces between the between the molecules will have a high effect on the boiling points. That is, the attractive forces between the molecules will have an effect on their boiling points. Now, if we talk of solubility, then what we've seen is that in carboxylic acids, it has two polar groups, OH and carbonyl group, and hence it will not be soluble in non-polar solvents. Please remember, like dissolves like. So they will be soluble in polar solvents. So when I say they will be soluble in polar solvents, and what we see is that since carboxylic acid is capable of forming hydrogen bonds with water through oxygen, the oxygen on the carbonyl group, and even through hydrogen of the hydroxyl group, it forms extensive intermolecular hydrogen bonding. And because of this intensive intermolecular hydrogen bonding, lower acids like formic acid, acetic acid, propanoic acid, and butyric acid are soluble in water. Whereas when we talk of valeric acid and caproic acid, which are having 5 and 6 carbons respectively, are partially soluble in water. And then what we observe is that as the non-polar hydrocarbon part increases, the solubility decreases, and what we find is caproic acid having 8 carbons, caprylic acid having 8 carbons in it, is insoluble in water. And this we've already observed, that if we talk of oil, which is a ester, they are also insoluble in water. And when we dissolve oil in water, or when we dissolve either of the fatty acids in water, we get 2 distinct layers. So we'll take a short break here, and then we'll continue with the acidity of carboxylic acids. Thank you.
With this note, thank you, ma'am. Thank you so very much for giving us this session. Friends, you are requested to be with us as we are back after a short break. Thank you. Hello friends, welcome back to this session. Friends, as you know that today we are talking on carboxylic acids. In our previous session we discussed on methods of preparation as well as physical properties of carboxylic acids, and as promised we are going to talk on acidity trends. So here we are to discuss on acidity trends, and for the discussion of the topic we have with us in our studios Dr. Aparajita Chauhan. Dr. Aparajita Chauhan is Associate Professor in Department of Chemistry, Sri Aurobindo College, University of Delhi. Friends, if you wish to ask questions pertaining to today's lecture, then do call us through our toll-free number. Our number is 1800110430. I repeat, our number is 1800110430. Now I would like to welcome our guest Dr. Aparajita Chauhan once again. Hello ma'am.
Thank you, ma'am. If we talk of carboxylic acids, then the most important chemical property of carboxylic acids is their acidic nature. Carboxylic acids are more acidic than any other organic compounds, that is, they are more acidic than alcohols and phenols. But at the same time, they are less acidic than mineral acids like hydrochloric acid, hydrobromo acid, sulfuric acid and nitric acid. This is because mineral acids dissociate completely in water, whereas carboxylic acids dissociate partially in water. So when we talk of the acidity of carboxylic acids, the question arises, why are carboxylic acids acidic in nature? Carboxylic acids are acidic in nature because the OH bond cleaves to give proton in water, and the cleavage of this OH bond is made easier because of the presence of the two electronegative atoms in the carboxylic group. The two electronegative oxygen atoms of the carboxylic group weaken the OH bond by distorting the electron cloud by inductive effect, that is the minus I effect, thereby weakening the OH bond. When this bond, the OH bond, becomes weak, the molecule becomes less stable and it gives off its hydrogen atom as proton. And what we observe is that the equilibrium shifts towards the right of the reaction, towards the right side, that is, unstable acid dissociates more to give us a carboxylate ion. And now we will compare the stability of the resonating structures of the carboxylate ion and the carboxylic acid, and we find that the carboxylate ion is more stable as compared to carboxylic acid here. So what we find is that when I'm saying that this carboxylate ion is more stable, what we mean by saying so is that the negative charge is delocalized over two oxygens, and these resonating structures are equivalent. Whereas when we look into the resonating structure of carboxylic acid, then what we find is that one of the structures there is charge separation, and since it has charge separation, this is not that stable and it does not contribute much to the resonance hybrid. So what we find is that since it is less stable, the carboxylic acid is less stable, it has tendency to lose proton and convert itself into a more stable carboxylate ion, and hence the equilibrium shifts towards the right hand direction. So when we talk of the acidity of carboxylic acid, the 2 points that we have to keep in mind are, first, the dissociation of the OH should be easy, that is, anything which will help in dissociation of the OH will help in the acidity or will enhance the acidity of that molecule. And second, if the carboxylate ion formed is stable, the stability of the carboxylate ion contributes towards the acidity, and hence carboxylic acids are acidic in nature because the cleavage of OH bond is easy, and second, the conjugate base is stable. So now if we look into this reaction, what we find is that carboxylic acids dissociate in water to form a carboxylate ion and a hydronium ion here. And now if we look into the Ka, that is the equilibrium constant, which is the dissociation constant for an acid, we find it gives us the carboxylate ion and hydronium ion on one side and the carboxylate ion on this side, and it is showing us the degree of dissociation. And what we find is higher the value of Ka, that means that compound will be more acidic. Now the second point that we know is that is pKa is associated with equilibrium constant by saying that pKa is the negative logarithm of Ka, and generally we express the acidity of an acid in terms of pKa, and since pKa is the negative logarithm of the equilibrium constant Ka, lower the value of pKa, more acidic the acid will be. So now what we talk of this, when we discuss this in terms of pKa and Ka, so what we find is lower the value of pKa, stronger will be the acid. So if I say that carboxylic acids are weaker acids than mineral acids, what I mean here is that the pKa of carboxylic acid will be higher than mineral acids. For example, the pKa of a carboxylic acid is 3.5, whereas we know that the pK of mineral acids can be 0 to 0, 1, and hence these carboxylic acids are weaker acids than mineral acids. Not only this, these carboxylic acids are stronger acids as compared to phenols or alcohols, because pKa of a carboxylic acid is 3.5, which is lower than that of phenol, which is 9.95, and which in turn, and pKa of acid is really lower as compared to alcohols, which is the pKa of alcohols ranges between 15 to 8. So on the basis of pKa values, we can say that the most acidic are mineral acids, followed by carboxylic acids, followed by phenols, and then alcohols. Now the question comes that when we talk of acidity of a carboxylic acid or an alcohol, we say carboxylic acids are more acidic. Why is it so? We know the acidity of a carboxylic acid or acidity of an alcohol is due to the cleavage of this OH bond. And what I've already explained here is that since the negative charge, we have two electronegative oxygens here, this bond between O and H is highly weakened, and acid gives proton more readily as compared to alcohol. Not only this, when we compare the conjugate bases of the two, that is, if I talk of an alco oxide ion, then what we find is, now if we look into this energy diagram here, then what we find is that alco oxide ion is less stable as compared to the carboxylate ion, because in alco oxide ion, alkyl group exerts a plus I effect, due to which there is localized negative charge on oxygen, and this is less stable. Whereas when we talk of the carboxylate ion, the negative charge is delocalized over two oxygens, thereby stabilizing the carboxylate ion, and since this is more stable, the carboxylic acids are more acidic than alcohols. Now if we compare acidity of an alcohol and phenol, then what we find is that acids dissociate to form a carboxylate ion, whereas phenol dissociates to form a phenoxide ion. And when we talk of the phenoxide ion, by mistake we've not shown it here, what we find is that there is this oxygen gives its lone pair of electrons to the phenyl ring, as a result of which this oxygen has a positive charge and these carbons have a negative charge. So there is charge separation between this, and the phenoxide ion although being resonance stabilized, it is less stable as compared to the carboxylate ion, which is more stable because the contributing structures are equivalent, that is, negative charge is spread equally over two oxygens, and hence carboxylic acids are more acidic as compared to phenol. Now, if we look into now let us concentrate on the acidity of carboxylic acids. So now we know that if we are talking of an acidity of a carboxylic acid, phenol and an alcohol, then what you have to remember is that carboxylic acid is most acidic, followed by phenol and then alcohol. Now, if we concentrate on carboxylic acids further and we see what is the effect of substituent on acidity of a carboxylic acid, then what we find is that if an electron donating group is present at the alpha carbon, or an electron donating group is present in the carboxylic group, it will decrease the acidity of the carboxylic acid because it will decrease the stability of the carboxylate ion due to minus I effect. Hence, because of plus I effect, and because of this plus I effect, the negative charge will increase on the carboxylate group and this will become unstable. Whereas if we have an electron withdrawing group, then this electron withdrawing group will withdraw the electrons from the carboxylate group and will stabilize it, and hence it will increase the stability or increase the acidity of the carboxylic acid. That means any group that will increase the negative charge on the carboxylate ion will destabilize it and hence decrease the acidity, whereas an electron withdrawing group will stabilize the carboxylate ion and increase its acidity. Now, supposing we have substitution at the alpha carbon here, and we replace this carbon with an electron withdrawing group here, that is halogen. This chlorine exerts a minus I effect, and because of this minus I effect, it will pull the electrons towards itself from the carboxylate ion, thereby stabilizing it. Not only this, first it will pull the electrons towards itself, further weakening the bond between O and H, and this H can be given off easily. Not only this, it will further stabilize the chlorocarboxylate ion because of the minus I effect here, because it will help in dispersing the negative charge. Now, what we observe is that if we replace another hydrogen with a halogen, this will have a further electron withdrawing effect, due to which this bond will weaken further and the cleavage of proton will be easy. Similarly, if we have three halogens, then what we find is that the cumulative negative effect, that is the minus I effect, will be so great that the dissociation of this OH will be really easy and it will greatly stabilize the trichlorocarboxylate ion formed. And this is also supported by the pKa values. What we find is that the pKa value of trichloroacetic acid is 0.64. That means it is highly acidic as compared to acetic acid, whose pKa value is 4.74. So what we have to remember is that if an electron withdrawing group is present, it will help in the cleavage of OH bond because it will pull the electrons towards itself, and second, it will also stabilize the carboxylate ion so formed. So the second point that we have to remember is the distance between the carboxylic acid and the substituent present. So the closer the substituent to the carboxylic group, greater will be the minus I effect. That means it will be able to disperse the negative charge more on the carboxylate ion, and it will become more stable and acidity will increase. So what we find here is that as this distance will increase, the minus I effect will decrease, and because of the minus I effect decreasing, the cleavage of this OH bond will become difficult, and the stability of the carboxylate ion will also be less. So since this chlorine is present on the alpha halocarbon here, the cleavage of the OH bond will be most easily here, followed by when the halogen is present at the beta carbon, and then when it is present on the gamma carbon. And this is again can be correlated to the pKa values, that is the pKa value of alpha chlorobutanoic acid is 2.86, whereas that of gamma is 4.52. So what we observe here is that as the distance between the electronegative atom and the carboxylic group increases, the acidity decreases. Now we have to look into the effect of electron donating substituents. So when an electron donating subgroup is present next to the carboxylic group, it makes the removal of proton difficult. So what we find here is that if we compare the acidity of acetic acid and formic acid, acetic acid is less acidic as compared to formic acid, because acetic acid has a plus I effect, and because of this plus I effect, it increases the electron density on the carboxylic group, due to which the cleavage of the OH bond becomes difficult and release of proton becomes difficult. And whereas in this case formic acid, there is no alkyl group, so the release of proton is easy. Second point what we note here is that the carboxylate, the acetate ion formed from acetic acid, is less stable as compared to the formate ion, because the methyl group in this, because of plus I effect, increases the electron density on carboxylate ion, thereby destabilizing it. And what we find is that formic acid is 10 times more acidic as compared to acetic acid. So what we find that as the size of the alkyl group becomes larger, the plus I effect will increase, and since the plus I effect will increase, the dissociation of OH bond will become difficult. At the same time, the stabilization of carboxylate ion will also be less, and acidity will decrease. So what we find here is that if I talk of a butanoic acid, then butanoic acid is least acidic and formic acid is most acidic. And now if we have to talk of isomeric alkanoic acids, then what we find is that as the branching increases, acidity decreases, because as the branching will increase, the plus I effect of the alkyl group will increase, which will make the deprotonation difficult, and it will also destabilize the carboxylate ion. So what we find is that electron donating groups will decrease the acidity, whereas electron withdrawing groups will increase the acidity of alkanoic acids. Now let us compare the acidity of some typical carboxylic acids. So what we find is that if we talk of unsubstituted alkanoic acids, then formic acid is most acidic, whose pKa value is 3.75. And if we talk of halosubstituted acids, that is fluoroacetic acid, chloroacetic acid, bromoacetic acid and iodoacetic acid, between these the fluoroacetic acid is most acidic, because fluorine, being the most electronegative among halogens, will exert maximum minus I effect, thereby helping in the cleavage of OH bond as well as stabilizing the carboxylate ion. And then what we see that if we are comparing between dichloro, trichloro and monochloro, then what we find is that trichloroacetic acid is most acidic. Whereas if we talk of an unsubstituted acid again here, which is propanoic acid, it is least acidic because the alkyl group is larger here and the plus I effect is more. On the other hand, methoxy group, which will again exert a minus I effect, it will increase the acidity of the carboxylic acid, but not so much as the halo-substituted carboxylic acids. Now let us compare the relative acidic strength of an aliphatic acid with an aromatic acid. What we find is that benzoic acid is less acidic than formic acid, but it is more acidic than other alkanoic acids due to the presence of the phenyl ring. The carboxylic group, which is attached to an sp2 hybridized carbon, dissociates to a greater extent because sp2 hybridized carbon has a greater minus I effect as compared to a sp3 hybridized carbon. So the phenyl ring exerts a minus I effect, due to which the bond between the O and H becomes weak and it undergoes dissociation more easily. Second point that we find is that the carboxylate group undergoes resonance with the phenyl ring, thereby stabilizing it, and benzoic acid is more acidic than acetic acid. So what we find here is that the pKa of benzoic acid is 4.2, whereas pKa of acetic acid is 4.8. Now let us look into benzoic acids, but before going further into acidity of substituted benzoic acids, let us keep in mind that if they give us unsubstituted acids, then formic acid is most acidic, followed by benzoic acid, because in benzoic acid the carboxylic group is attached to a sp2 hybridized carbon, and then it is followed by other alkanoic acids. And if we talk of substituted alkanoic acids, then electron withdrawing groups will increase the acidity, whereas electron donating groups will decrease the acidity. Now let us see what will be the effect of substituents on the acidity of benzoic acid. The effect will be same, that is, if a group is a electron withdrawing group like NO2, CN, COH and halogen, then what we find is that these will increase the stability of the carboxylate ion through minus I effect, whereas the electron releasing groups will decrease the acidity of the substituted benzoic acid because they will exert a plus I effect, and at the same time they may also exert a plus I and a plus R effect, which will make it, the substituted acid, less acidic than benzoic acid. So let us look into few examples here. So what we find here is that if I compare the acidity of paramethoxy benzoic acid to nitrobenzoic acids, then what we find is that paramethoxy benzoic acid is less acidic than benzoic acid, because here this will destabilize the carboxylate ion because of the plus R effect. It is exerting a minus I effect also. The methoxy group exerts a minus I effect, but because of the distance from the carboxylic group, the magnitude of minus I effect will not be so large as compared to the magnitude of plus R effect, and due to plus R effect the electron density on the carboxylate ion will increase, hence this will be less acidic than benzoic acid. Whereas if we compare the acidity of nitro acids, then what we find is that orthonitro benzoic acid is most acidic, because the nitro group will exert a minus I as well as minus R effect when it is present at the para and the ortho positions. So similarly here again I have taken another example in which I have compared the acidity of toluic acid with benzoic acid, parachlorobenzoic acid and para-nitrobenzoic acid. So what we've done in this case is we've taken the substituents at the para position. So when we take the substituents at the para position, so that means we will be, the inductive effect will be almost the same, because the magnitude of, since all the groups are present at the para position. So now what we find here is that when I talk of this group here, this methyl group will have a plus I effect, and due to this plus I effect, it will increase the electron density on this negatively charged carboxylate ion. At the same time, it will also have hyperconjugative effect, which will further destabilize the carboxylate ion. Whereas if I talk of a halogen, then please remember halogens have a plus R effect but a minus I effect. And in this case, minus I effect will predominate, because minus I effect in case of halogens is stronger than the resonance effect, and this is stabilized because of minus I effect. But the nitro group stabilizes the carboxylate group further because of the minus I effect and the minus R effect. So what we find is that this nitrocarboxylate ion is most stable, followed by chlorocarboxylate and paratolic acid, carboxylate ion of paratolic acid, which is paratoluate, will be least stable. Hence the order of acidity will be that para-nitrobenzoic acid will be most acidic, followed by para-chlorobenzoic acid, and least acidic will be the tolic acid. In our next lecture, we shall be discussing the comparison of acidic strength of isomeric substituted benzoic acids. And with this we'll wind up today's lecture. Thank you.
With this one, thank you, ma'am. Thank you so very much for giving us this session on carboxylic acids. Dear friends, you are requested to write to us at info.cc@nic.in if you have any query or feedback. We are going to meet again very soon. Till then, take care. Goodbye. Thank you.
Thank you.